Hi everybody. This video is going to be a very kind of high level overview of Matlab, as well as how to use it, kind of a tour of Matlab, and then I'm going to go through sort of the key Matlab skills that you'll need to make high quality figures for your lab reports, as well as handle all of the analysis that you might have to do for a lab report. All right. Um, so you should be able to install MATLAB on your local laptop or computer through the university website for software. So we have a university level license for MATLAB, which means that you get to use MATLAB for free on your computer. And I have all the instructions for doing that in Moodle. Okay, so once you have your MATLAB installed, it's going to look like this when you open it up. Right here, this top panel right here is where you're going to do your code writing. Here is your command window, so you can kind of talk to MATLAB and MATLAB will talk to you through this interface here. This pane on the left gives you your folder structure. And then over here is your workspace where you will see all of the variables that you use in your code populated along with their value or general information about that. Okay. You're going to want to make sure that you are in the editor tab because we're going to need to make use of these buttons up here. And so to start with, it's always good practice to make sure you kind of start with a very fresh start with every MATLAB code that you're working with. So I always put myself in the habit of closing any open windows that MATLAB might have, clearing all of the command window spaces, and CLC will also clear out your workspace. So this basically, if you're already in MATLAB doing something different, this will basically give you a fresh slate. So I encourage you to just default put this at the very beginning of all of your scripts. Okay, so after we've done that, what we want to do is we want to put into MATLAB the data that suppose we've collected in the lab. So for example, let's say that we've collected temperature and viscosity data. All right, so what I'm doing here is I am just giving each of these variables a name. I like to make sure that I name my variables in such a way that when I look back on it, or if somebody else looks at it, it's very clear what I'm doing. And then we're going to define a vector using square brackets, and then we end each line with a semicolon. This is just MATLAB syntax. If you do not include the semicolon, it's going to print it out to this command window. Okay, so we're going to store our lab data in vectors. This is very similar to how you would store your data if you're working in Excel, kind of as a row or column of data. And so I'm going to just type this in. So we're going to suppose that we've taken 5 measurements at 20, 30, 40, 50, and 60 degrees. And I'm going to make a comment in here that this is degrees Celsius. All right, so using this percent symbol is how we make a comment. So it turns green when that happens. That means that the code does not read it. It doesn't do any processing with anything beyond the percent symbol. So this is just notes to ourselves or to anyone else who might be looking at our code. So I highly recommend putting in comments. My comments to my future self have been helpful in the past. So I'm going to put in here, this is the data collected from the lab so that I know that. And then we're also going to put in viscosity. And 36.3. This is just made up data at this point. And the units on viscosity is millipascals times seconds. So this is dynamic viscosity. Mu is the symbol that it's given. Don't worry too much about that. You'll learn all about it in 3500 if you are a mechanical engineering student. Okay, so we have some data in here, and I want to show you kind of what happens next. So if we click run, we're going to be prompted to save this file, which I will at this point. So I'm going to call this MATLAB demo. You can call your files whatever makes sense to you. All right, and so now it's saved, so now we can run it. I have semicolons here, so it's saving these two variables in my workspace. We see them show up here now, but nothing shows up in the command window. So if you recall, the semicolon basically tells MATLAB, don't print this to the screen. If we take it off and run it again, we can see that we have our temperature data and our viscosity data. And you can see here that it's stored as a row vector. If we want to, store our vectors as column vectors, we can just put a little apostrophe on the end of the line, and we'll see that it stores it column-wise, right? Alternately, if you want this format, you can, instead of putting commas between the entries, you can use a semicolon, like so, and here. So I'm going to take off the semicolon so we can see it. I don't have that apostrophe or the transpose symbol at the end of this now, and you'll see it looks the same, right? So those are the two ways that you can get column data versus row data. It doesn't matter too much which way you do it, but I just wanted to make you aware. Okay, so if we say, okay, we need to plot our experimental data. So let's do that in a very basic way, and then we're going to make it look nicer and nicer with adding a few kind of key elements. All right, so the first thing we want to do is we want to name our figure. I'm going to call it Fig 1, and I'm going to say Fig 1 is a figure. So I'm just telling MATLAB, please open up a figure. All right, and so if I run this code, here's what happens. I've opened up a figure window, but you'll notice obviously there's nothing in here because we haven't told MATLAB what to put in the figure just yet. All right, so let's go ahead and do that now. So the first thing that we can do is we can say, all right, I want to make a plot, and I want to plot temperature against viscosity. All right, so let's run that now. Okay, so we have a figure technically here with our data on it. There's a lot of things wrong with this, obviously. So this is experimental data at discrete points. We do not want to connect them with lines like this. This is disingenuous. We don't actually have information about what's happening in between the data points that we collected in the lab. So we want to make sure that we're plotting this as discrete points rather than having a line connecting them. All right, so let's change that first. And to do that, I'm going to say I want a circle to be plotted. All right, and let's see what that looks like. Okay, so now I have circles indicating my experimental data in here. You'll notice that the default color is this kind of bluish, and the markers are kind of small. All right, so let's fix that. I like to make my plots wherever possible in grayscale, so using values between black and white, so that it's easy to print and is distinguishable no matter what kind of screen you're looking at or how you printed it on paper. So the color designation for black is letter K. R is red, B is blue, G is green, C is cyan, so on and so forth. You can Google this on MATLAB's page and you can get a full list of how to do colors. But right now I'm going to say I want a black circle. All right, so that's great. Now our circles are colored black, but they're still too small, right? So let's make them a bit bigger. So I can do marker size. Marker size, and I'm going to make it 10 point. All right, so this is going to make our markers quite a bit bigger. All right, so that's much more visible. That's good. But the line thickness could be a bit heavier, I think, to make it a little more legible. So I will use line width, and I will say I want the line width to be 2-point font, 2-point size. All right, so now let's have a look. Very good. All right, so these are very clearly distinguishable points. So we've got that in there. And let's go and look at this once more. Okay. We also should note in here that now that we have our symbols for our experimental data, that's very good. Our axes still need quite a bit of work. The font is too small, there's no axis labels, and so on and so forth. So let's fix that up now. And so we're going to do that by the following. So we are going to set all of our plot features. All right. And this is all going to go into this set function. And this little ... allows us to write things on the next line, but it's still in the same. MATLAB still recognizes it as if it were one continuous line. So it helps us be a little more organized with our formatting in the plot itself. Okay, so I'm going to say I want the box on my plot to be on. And I want my x-axis to have minor tick on. Same thing with the y minor ticks. We're going to keep those on. Line width. Oops, I need the little, there we go. Line width is going to be 1 point. And our Y grid, we're going to set to be off. You can also turn this on here if you want. Any of these things you could also turn on. Font size, I will set to 20-point font. So this lets us rescale our plot in our report. And if we shrink it down, the axis labels don't get too small. Font name, I would suggest Times New Roman. So it matches, but just make sure that you match whatever is in your plot currently or in your report currently. So whatever font style you're using, make sure it matches in your plots. All right, and so look at that. We have our box around our figure. We have our axis labels in the right font and much more legible now. But we still need to add some labels. And I also want to change the color. So I'm going to set the color of the background of my plot to just be white. And the color for white is 111. So this is the RGB color that you give to MATLAB in a 3-component vector. All right, so let's have a look at that. All right, so this used to be gray in this background before, now it's white. So when it saves this figure for us that we can use to put in our lab report, it's already ready to go. And we don't have that ugly gray in the background. Okay, so now let's add our labels. All right, so we want to label our x-axis as temperature, and then we want to give the units. So we have degrees C. All right, and I just want to show you what this looks like before we pretty it up a bit more. And then on the vertical axis, we have viscosity. And it has units of millipascals times seconds. All right, so let's see what this looks like. Okay, so we have our axis labels in here. It's the correct font, right? But this is not what we want for our lab reports, right? We don't want to show this dot or the asterisk to imply a multiplication. The degrees on degree C should be in a superscript, of course. So let's fix this. And the way to do this is we are going to tell it to use an interpreter called LaTeX. All right. You can think of, I spelled interpreter wrong here. Interpreter. You can think of LaTeX as basically math mode. And to go into MATLAB or to go into math mode, we're going to need to use the $ around anything that we want in MATLAB in math mode. All right, so I want this to be an exponent, so I will use the caret. And then for this multiplication dot, C dot is a center dot, so it's like a vertically centered dot. All right, and I've put the $ around each of those math mode things. So let's see how that looks. Much better, right? So you'll notice that anything that I put with the $ around it has gone into a math mode typeface. It's allowed me to use the caret, and then now the caret doesn't show up anymore. It just puts that O in the superscript. Okay. If you have questions about a certain type of thing you want to do in MATLAB in math mode and you don't know the syntax for it, you can just Google this. There's lots of references online. So for example, if I want to instead use the symbol for viscosity, this is the Greek letter mu. Again, I've put it around with the $ and it looks like this. All right, so it converts basically that code into the typeface that we want for math mode and the symbols and so on and so forth. All right. Okay, great. So this plot's looking pretty good, but we need to add uncertainty and we want to put in error bars. All right, so let's talk about how to do that. So I'm not going to go through uncertainty calculations. You certainly can do uncertainty calculations in MATLAB. One thing that I will mention that you want to do is you will often have to do kind of term by term operations. So for example, if I wanted to say what's temperature times viscosity. All right, so if I wanted to do this operation, there's an issue with just doing a straight multiplication. This is going to multiply them in like a vector multiplication way. And so we don't want to do that. We actually want to do term by term. So we will do dot times. Okay. And you will have to do this for any type of multiplicative or division type operation. Like if I wanted to do viscosity squared, if I want to square each individual element in the viscosity vector, I would do a dot times the caret, or a dot and then the caret, sorry. All right, so let's just mention that we have our uncertainty. Here is the uncertainty calculated. Obviously, you'll have to calculate this yourself, but assuming that you've done that, I'm going to just put in some dummy data here. So I will have the same number of entries as I do for our raw data. All right, and so I'm also going to show you, so if I have these values and they are, perhaps we need to change the units on all of these and increase by a factor of 10. I would do dot star 10 to multiply every entry in here by 10. Okay. All right, so this is our error in the viscosity. That's our vertical error. And then we're going to have horizontal error as the same thing for every single entry. So let's say that it's 2 degrees for every single temperature. That's our error. So I'm going to say 2 times 1's 5, 1. All right, so 1's 5, 1 is just a 5 by 1 vector of 1's. So if I do this, there's my error, right? Or there's my vector, 5 entries in a single column, all with the value of 1. And then when I multiply this by 2, I'm multiplying each of those 1's by 2. All right. So we will have a vertical vector of just 2. Okay, fantastic. So let's add our error bars. Okay, so if we want to change this plot to have error bars, I'm going to format this a little bit differently. So instead of using plot, I'm going to use, actually, I'll keep that on. And if I'm going to add more than one plot, I need to tell MATLAB Don't replace the plot you just did and do the new one over top of it. I need to say hold on. And then at the end of all my plots, I'll say hold off. All right. So that basically says, hang on, I'm still adding things to my figure. Don't overwrite the thing you did in the line before. Okay. If you don't have hold on and hold off on here, you'll essentially keep overwriting the plot that you did last, and you'll only have one curve, and it'll be the last one that you had done in your code. Okay. So be careful of that, because it's very frustrating when that happens. Okay, so I'm going to add error bar. This is a built-in Matlab function. And I am going to do, again, temperature versus viscosity. And then I need to tell Matlab the bottom vertical error, and then the top vertical error, and then the bottom or left side horizontal error and right side horizontal error. Since our error bars are symmetric, so we're basically saying the error is this plus or minus the same thing. We're going to basically do the following. So we're going to have our vertical error twice. So this is our plus vertical error minus vertical error, and then our horizontal error twice too, like so. Now, you could change these if you had cause to have the error bars be different on either side of each symbol, in which case you would need to have two different error vectors for the horizontal direction and then two different ones for the vertical direction. All right, and we still want this to be markers that are circles with black, and then I want to keep all of this typesetting as well. So I want to make sure that my marker size is still size 10 and my line width is size 2. All right, so let's see what that looks like. All right, great. So now I have error bars on here. So this is essentially a finished plot of what our experimental data should be if we were comparing viscosity versus temperature. All right, so we've got error bars for both measured quantities. They change depending on the measurement for the viscosity. So that was based on our uncertainty calculation. And then our temperature error bars are the same for each temperature because that is a consistent error. All right. Okay. So this is now finished. I want to show you another type of plot. So I'm going to carry this over. And actually, I find myself copying essentially this section. This is the beautification of our plot. I find myself copying that and reusing it over and over and over and over again. So feel free to do that yourself. And so now I want to make a new figure for you. So I'm going to call this figure 2. This will open up 2 windows for a figure now, and I'll show you that now. So I have figure 1, figure 2. They're the same thing right now. Okay. I want to show you an alternate way of displaying the error. So instead of doing these error bars, we can also do an error band, which is essentially a curve on the top and the bottom that follows where the error is. And then also, I'll show you how to shade between those lines. Okay, so here's how we will do that. So we're going to take off our error bars because we don't need them anymore. We're going to shade in the error instead. But first, we need to compute what the error bounds are. So we have an upper bound is equal to our viscosity plus our vert error, right? So this is essentially our measured value plus the error going up. And then our lower bound is viscosity minus our vert error. Okay. So I can plot both of those curves. So I'm going to plot temperature versus our upper bound. And for this one, I want to have a black line. I don't want to do symbols this time. I want to do a line, and I want to make that line dashed. So I'm going to do K for black, and then dash dash gives me a loosely dashed line. I don't have markers anymore, so I don't need to say anything about marker size, but I want to keep my line width consistent. So I'm going to keep this to be 2. And then I want to do this exact same thing, but I want to do that for the lower bound. Oh, MATLAB is case sensitive, so if you have a lowercase l, you got to keep a lowercase l down here. And let's run that and see what we have. Well, this is not what I intended. And it looks like that we have a dimension problem. So let's look at our size. So down in my command window, I can ask MATLAB, what is the size of upper bound? Because that seems not correct. Oh, we don't want something that's 5 by 5, right? So let's figure out what's happened. So we calculated upper bound by adding viscosity to vert error. So let's look at what viscosity looks like. So we have a vertical vector here, and then our vert error is a horizontal vector. All right. So what's happening is we are populating a 5 by 5 thing since our formatting for those two vectors is different. So we can fix this by making sure that this is also a column vector. All right. So I've just added these apostrophe marks here to make a column vector. All right. And now that fixed it, right? So now we have what we'd expect. All right, so let's just compare side by side. So we're basically saying the same thing in both of these plots, just in a bit of a different way. All right, so here is our bound for our measurement error. And then we also have our bound for our measurement error shown as error bars here. Okay, what's often very nice to do is shade in this region between our two lines here. And that is a little bit tricky, but I will show you how to do it. So what we're going to do is the following, and I'm going to put this first. So one thing that's important to note about MATLAB is when you plot things on the figure, it respects the layer. So whatever you put first is going to be on the bottom, and then the last thing will be on the top. So I want to make sure my symbols and all of that good stuff is on the top of my plot, and so I want my shading to be in the background, essentially. Okay, so what I'm going to do is I am going to say, I have some variable. I'm going to call it x2. And this is my temperature. And then I'm going to flip left to right. So flip LR is flip left to right temperature. If you ever want to see what a function is doing, you can do it down here. So I already have temperature as a variable, right? It shows up in my workspace. So if I want to see what does flip left right temperature do, it does this. Hang on a second. Oop. Okay, so also to note, you can push your up arrow on your keyboard and you can see all the past things you asked in the command window. So this flip left right only really does anything if we have a row vector. So I'm going to fix that right here. All right, so you can see it just flips left to right all the entries in the temperature vector. Okay, and then we want to define what the in-between region is. So we're going to choose our upper, let me see. Where did I put it? Upper bound. Actually, I put this in the wrong plot. We want to do this on our second one. Sorry about that. So I'm just gonna move it over here. So I'm gonna put this right here. So I'm gonna make the in-between area that we want to shade between the upper bound and flip left right of our lower bound. And I need to make sure it's a column or a row vector. So let's just check. Yep, so we need to transpose that one with our little hash sign. All right, and then I want this to be a gray color. So I need to define a gray color in MATLAB. That's not a default color that MATLAB gives us to work with. So black is a standard color that MATLAB assigns the symbol K. So we can just use K and we get black, and that's fine. Gray is not that way. So gray you get in the RGB color. So this is an RGB vector like this. And you can define any color that you want, right? As long as you have the RGB coordinates for that. Gray is any color that has all the same value for each of the three. So I'm going to choose 0.7 and apply that to each of these. I like to do it this way. So if I want to adjust the style of gray, I can just change one number rather than all three. Okay. All right, so we have our color we want to do, and we kind of have defined the variables that we need to fill in between those two lines. So we're going to fill, and we're going to fill between x2 and then our in-between variable. And we're going to assign it this gray color. All right, so let's see what we get. Oh, you know what? Okay, so this is how errors are going to display in Matlab. So it'll tell us exactly what line it is. If you click here, it'll take you there, which is kind of right in front of us anyways. These need to be in the same format. So we need to make sure that the temperature, so before we had temperature was vertical, we need both of them to be column vectors. All right, so let's do this again. All right, cool. And so now we have our shaded region between our two lines, and then I have outlined our error region with this dashed line. Something else we might want to consider to really make our data points stand out is we might want to change our marker face color so that it's not just transparent. So I might suggest white. So this is marker face color, and then W gives us white. So let's have a look at what that looks like. All right, so we filled in our experimental points with the white line, and now they really pop. Okay, the next thing we might want to add to our plot is a legend. All right, and so to do this, I am going to use a legend. And I'm going to call it L. So this is a legend. And we want to put in entries in the order that they appear. So we have our fill is first. Which is, oh, sorry. Let me do down here. So, okay, I'm going to do my legend right here. So as long as it's after when you've plotted your data, that's fine. So our first one is our fill. This is our first plot. So this is going to be region of uncertainty. Our next one is going to be experimental data. All right. And so let's see what we get when we do that. All right, so here we have our legend up here. We've called out our region of uncertainty and our experimental data. Typically, I like to turn off the box because I just think it looks nicer without a box. So I can say box off. All right, so if I do that, then I get rid of the box around here. And I think that looks a little bit better. Okay. The last thing that I want to show you is how to fit a curve to your data. So let's replicate our first figure that we did here. And I'm going to add some space down here. So you're free to add as many empty spaces as you want to make this more legible. Matlab doesn't do anything if there's nothing typed here. So it's no big deal to have spaces. That's completely fine. All right, so I've added another figure. I'm going to call it figure 3. All right, and this time I want to find a curve fit. Oops. Of the form mu equals some constant a times the exponential of b divided by t. All right, so essentially I know what the shape of the function should look like, and I know there's two coefficients that I want to fit. And so that is what I'm going to try and do. And so what I'm going to do is I'm going to define some fit options. I'm going to call them fit FO for fit options. And I'm going to say for the method of fit, I will use nonlinear least squares. The next option I'm going to define is my lower limit. I'm going to start at 0, 0, for example. My upper limit is going to be infinity for, and then max of my temperature. Go to the next row for readability. And then my starting point for finding A and B is going to be 1 and 1. All right. Okay. Now my fit, I'm going to call FT, my fit type. I'm going to tell MATLAB, I want it to look like A times exponential of B divided by X. And the coefficients that it needs to fit are what I've called A and B. All right. And then the options that I want it to use are FO. Technically, you could include all of these options inside this one line, but this is a little bit tidier. Also worth noting here, MATLAB is really helpful kind of within MATLAB itself. So if I was like, I don't remember what the arguments for fitting is, I could say help and then fit type. And inside of my command window, it's going to give me some examples of how to do this, the different syntax and options, and a description of what the function does. Okay, so this is a great tool. If you get stuck, you can always type help and then the thing. If it doesn't pull anything else up, I would suggest using the MATLAB website, or Stack Exchange is also a really helpful tool. And you'll find folks and lots of posts on the discussion forums in both of those places that will, chances are, have something that's pretty close to whatever issue you're having. Okay, so now I want to say that my model, and then I need to also save, some stats about the model, which I'm going to call GOF. And we're going to say fit. We want to fit the temperature and the viscosity using our fit type FT. All right, so let's run this and see what we get. Okay, so figure 3 we haven't changed yet. Figure 2 is the same and figure 1 is the same. That's fine. Before we printed figure 3, you'll notice I left the semicolon off of here. All right, so that means that it's going to plot, or it's going to print out here what my model is. Okay, so I am going to use this information to basically put this model onto our experimental data. So I'm going to say, okay, A is 25.59 and B is 42.1. Fantastic. And now I want to make a curve that's nice and continuous over where the range of my data is, or maybe past it, right? So if you remember, we collected data from 20 to 60. So I'm going to extend my model fit from, let's say, 10 to 100 degrees C. So continuous. So I'm going to make a variable called temperature continuous, and I'm going to say I want a linear distribution of points between 10 degrees C and 100 degrees C, and I want 1,000 points in there. Okay. And then I'm going to say my model is just A, my model coefficient, times the exponent, and this is a term-by-term multiplication, so I'm going to put that dot in there. My exponent of B divided by temp continuous. All right. Okay, so now I can add another plot on top of here that has my model. So I'm going to plot temp continuous versus the model. And I'm going to say, let's make this a red line that's solid. So no dashed. So if I just have one dash here, that gives me a solid line. And I'm going to keep my line width to be 2, just like the other one. Okay, so let's see what we get. Oh, so I have a spelling error, which I thought maybe I did. I'm missing a U here. Okay, so the other nice thing about MATLAB is if you put your cursor on a variable, it'll highlight all the places where it is. So that should have been my first indication that I had a spelling error. All right, and so here is my model. All right, and so we can play around with, how this looks. We can say, all right, well, what if we instead plot it from 20 to 80? All right, and so we can do that. All right. And so I think this is pretty much all of the kind of key things that you might need to use MATLAB for in terms of doing lab calculations, making lab figures, and all of that good stuff. The very last thing that I'm going to show you is how to save your data. So let's say that we want to save this figure to include in our report. What I'm going to do is I'm going to save it. The key thing is, so I'll call this figure 1. You can call it whatever you want. It defaults to saving it as a .fig. That's a MATLAB file type, so you won't be able to drag that into Word without issues. So I would suggest changing it to a JPEG or a PNG format. And then you save it. And then I can show you. So if I go to that folder, so here's my fig1.png. Here we have it. All right, and so we can use this just like any image, drag it into Word and carry on with our report writing. So I hope this was helpful. Please feel free to refer to this. I will also post this exact script onto Moodle alongside this video. And please let me know if you have any questions.